Now, let us commence our third session, Today's and Tomorrow's Sorrows, Storage and Global Warming. Our first talk is with Valerie Tomlinson and Ruby Satele. It is a recording where both will be featured. In the question and answer session, only Ruby Satele will be able to be present. Valerie Tomlinson is a conservator at the Auckland Museum, Tamaki Paenga Hira, and works on general objects conservation for collections, including on preventive conservation needs of the collections. She is of Canadian origin and received her master's in art conservation from Queen's University in Ontario. Ruby Satele is a Samoan woman born and raised in Aotearoa, New Zealand. She is a collection manager at Tamaki Paenga Hira Auckland War Memorial Museum and cares for Pacific treasures in the Human History Pacific collection. Her master's thesis at the University of Auckland focused on continuities and changes of Selu Samoa, Samoan combs from the 19th century.
Tēnā koutou, ko Valerie Tomlinson rawa ko Ruby Satele o Kuingwa, no Tamaki Makaurau mātou, ke Tamaki Paenga Hira. Hello, my name is Valerie Tomlinson, and this is my colleague Ruby Satele.
Talo falava.
We are from Auckland Museum in Aotearoa, or New Zealand as you know it, which is in the middle of the Pacific Ocean, known as Te Moana Nui a Kiwa in the language of this area. Auckland Museum is a collection of almost everything from War Memorial to Natural Sciences Museum to Applied Arts and History collection and archives, and includes one of the largest collections of Maori and Pacific cultural materials in the world. Like many of you, our museum is encountering more and more plastics coming in with acquisitions, and the point has been reached where we are needing to contemplate special storage for plastics. This presentation outlines our progress towards a special storage program for these types of materials. The items in our collection cover a wide range of objects, from fashion items of global Western culture to disposable ephemera such as plastic bottles, toys, and archival sound and image material. However, a lot of the plastics coming into our collections are from the Pacific Island cultures. New Zealand is in the Pacific Ocean, and many people from the smaller island nations have moved here. These Pacific peoples strive to maintain cultural practices wherever they are. For people that have moved to Aotearoa, New Zealand, traditional materials and resources are not easily available, so creators turn to readily available materials such as plastics as substitutes to continue and carry out traditional art. These images on the screen are of more traditional works, but they are using recycled, easily available materials, such as the traditional kete on the right, made of pallet strapping, or this hat on the left, made of recycled shopping bags. Other items cross the boundary from craft to modern art, where the artist has drawn upon their cultural roots in creating items such as this Fijian thiva novo or breastplate, traditionally made of shell, but here is made of kitchen Brillo scrubbing pads and plastic leaves. On the right is another one made of rubber snakes and synthetic hair, and on the left is a kete made out of photographic film, and a lei made of highly plasticized, rubbery synthetic fruit, flowers, and beads. I'm finding that many of these materials are highly prone to rapid degradation, such as the highly plasticized material or the hat made of shopping bags in the previous slide. In non-museum conditions, some of this material could be showing signs of degradation within a matter of a few years. Some of the plastics acquired are already showing signs of heavy degradation on arrival, such as this World War II map holder acquired last year, where the plastic overlay had turned opaque and yellow and is crumbling to the touch. I've been pushing for a plastics project to address the issue of plastics in the collection since a condition survey I did some years ago, where I had found degrading plastics that were crumbling to pieces, giving off odor, and even causing accelerated corrosion of other metal items in the same box. A particular type of filiform corrosion of plated materials or a powdery green corrosion of copper alloys seems to be more common in the presence of these plastics. This idea didn't really start to get traction until this acquisition came in. It contained dozens of items made of various plastic materials, including the pallet strapping previously mentioned, as well as brightly colored Christmas ribbon, candy wrappers, and some very fugitive plastics that were already crumbling to the touch upon arrival, despite only being a decade or so old. Even though this material was relatively new, we were already seeing yellowing, discoloration, and dirt being attracted to surfaces, mainly visible on the white and paler colors. One of the plastics types had become extremely brittle and was crumbling to even minor pressure. This rubbery type of plastic had visible spewing of plasticizers on the surface and felt sticky. And the silvery Christmas ribbon, you can see a fingerprint and loss of the metal layer happening here. Several other conservators have been adding to the pressure to address this problem, so we started to work out a plan. We started with researching plastics to find out which ones are the worst and which ones are relatively benign. In the end, the list of particularly problematic plastics was narrowed down to about a half a dozen types. Research indicated that although the ideal temperature, oxygen levels, humidity, and ventilation requirements varied from plastic to plastic, cold and or anoxic storage was the preferred option for degrading plastics in most cases. All plastics, and more generally all materials, will benefit from cooler temperatures and lower oxygen levels, which reduces both the oxidation rates and the rates of most chemical reactions involved in decay. Cooling reduces compatibility of low molecular weight additives in plastics so they can be forced out, but diffusion rates of plasticizers are also slowed down, so plasticizer migration rates generally decrease overall. Thermal expansion coefficients are higher in plastics than even in metals, so crazing, cracking, and separation of layers is a risk. As a result, slow cooling is preferred. From this research, the plan that developed was, first, research and acquire FTIR technology so that, among other things, we would be able to identify which was what material, and thus what the optimal environmental requirements for each was. Then separate the problematic plastics from the other collection material that may be affected by it. And third, store these plastics in an environmental condition that would reduce the rate of degradation. Generally, this meant cold anoxic storage for problematic plastics and regular collection storage for more stable, less harmful plastics. In addition, by separating out the materials that have the greatest need, we would extend the capacity of the storage space we have. Otherwise, our available cold storage space would fill up almost immediately. Our plan for a cold anoxic storage space grew out of earlier IPM developments at Auckland Museum, where anoxic treatment for pest management purposes had been created. Taking a segue into this seemingly irrelevant topic, I will describe how our IPM system developed. To start, the climate in New Zealand is subtropical with high relative humidity year-round and no season of freezing to put insect pests into dormancy, so many of our acquisitions were coming in pest-damaged, if not crawling with pests. We had a large walk-in freezer for pest management, but freezing was not suitable for all items, so I started researching into the purchase of a commercially available anoxic chamber. What I found had to be ordered from either Europe or North America, and the quotes I received ran about $100,000, and the chamber could process about a shelf load of books at one go. Fortunately, we have a resident engineering genius on our team at Auckland Museum, and he was enthused by the idea of creating his own system out of bits and pieces of equipment available in New Zealand. There was a lot of validity to this approach. Not only would the equipment costs be cheaper, but shipping costs would be zero. New Zealand being so remote from the rest of the world, not only is shipping hugely expensive, but maintenance is problematic, and this tends to limit what technology is available in the country. Fortunately, New Zealand has an international winemaking industry, and nitrogen generators are used in the winemaking industry. So our genius, Jed Weirin, took one of these nitrogen generators and combined it with easily available compressor technology. Then added a humidifier and a fan, added oxygen sensors for humidity, temperature, and nitrogen flow rate, and a central control panel. The climate-controlled nitrogen flow could then be connected to nearly any size or shape of container we wanted, and reduced oxygen levels to below 0.1% for pest treatment. He managed all of this for a quarter of the cost of the available anoxia chambers that I could find on the market, with vastly greater chamber capacity. Just to give you an idea of the flexibility of this system, I'll show you a couple of the pest treatments we've done so far. So the first treatment done with the system was to treat our entire painting and framed work storeroom where a possible wood borer outbreak had been detected. A shipping container was rented, and the entire storeroom was packed into the container. So we see packing, 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 packing. Oh, and remembering to escape before you seal yourself in at the end. So that's Jed there. Then creating a plug at the end with wood framing, which held the seal in place like a cork. Then starting the treatment running, and it all worked perfectly. The next treatment was the Maori cloak store. The cloaks had been in place for decades. They are relatively large, and many were very fragile, and building changes around the storeroom had made it impossible to remove the cloaks in the horizontal position. It was not deemed safe to tilt them upright to get them out the door for treatment, so they were done in situ. The nitrogen generator was placed in a small rented container outside the cloak store, and the nitrogen supply connected by a hose through the window. The whole shelving units were encapsulated and sealed in large anoxia bubbles. More sealing and the completed bubbles. I'll skip showing you other treatments because you get the idea by now. We've treated entire cars, whole rooms full of materials since then, and now it's time to get back to plastics. Well, the next genius idea of Jed's was to use the excess nitrogen stream from the nitrogen generator to create a cold anoxic chamber for plastics. The generator is capable of running continuously, and even the waste flow of nitrogen out the back of the anoxia treatment chambers could be reused for this. We felt it wouldn't matter if the nitrogen flow wasn't continuous, if the generator got shut off from time to time, as overall there would still be reduced oxygen and a reduced rate of aging. So the idea was to build a sealed chamber inside of one of our already existing cold stores and pump any excess nitrogen into it. With a few sensors and alarms and monitors, presto bingo, we'd have a cold anoxic storage room. Alternatively, we could even take a chest freezer and modify it to pump nitrogen in and make it into a sealed cold anoxic unit. However, at this point in time, COVID-19 entered our plans, which put an end to money for both the FTIR and the upgrades to the cold storage chamber. This is where Ruby enters the picture. She will run through what it is that we are actually doing instead.
As Val had mentioned, Pacific makers are innovative people, and using the accessible plastic materials is a growing element in their changing and ingenious art practices. As we all know it, some of the plastic can last a good number of years, some not so much. But whatever the time frame, plastics have properties that cannot withstand time, like wood or metal. So in 2019, a large collection of 51 items consisting of mostly hats and leis was acquired by the museum. A majority of this collection, especially the lei, contains plastic materials. Some of these are sturdy for now, but some are very brittle, and we handle these as little as possible. This is not the first acquisition containing plastic materials. However, the scale of plastic and involved has compelled us to look into alternative storage solutions. At the suggestion of Val, the decision was made to create a high-level anoxic microclimate packaging that will prolong or extend the life of these pieces. It is a bagging or bubble system where the packing unit is sealed in a barrier film bubble with ageless RPK. The initial stage of this packing is a standard one. Each pieces are individually nested and encapsulated in ether foam. There is a base foam and a top foam or lid with gripping system. The foam area that is in contact with the object is lined with Tyvek, and Dacron may be added for extra cushioning support. As there are a lot of uniqueness in this collection, nesting may take different forms as shown here. Individual packing removes any risk of gas and odor contamination. Each nesting are fitted in an acid-free cardboard box, and this is a standard for complete museum packing unit. This entire unit is bagged in a barrier film, which is sealed using a heat sealer. The barrier film are offcuts of the anoxic chamber that Val had previously mentioned. The advantages of this is that there are plenty in stock, they're accessible and sustainable. Unfortunately, they are not transparent in being able to see the object or the oxygen sensor. An ESCAR window could be put in place, but this increases the risk of air leakage. Ageless RPK are used to absorb the oxygen inside the bag. These are placed in the bubble before it is sealed. Because air is 21% oxygen, when the ageless absorbs all the oxygen, the volume of each bubble is 20% less. So there must be 20% more space in the bubbles than the size of the box. These will be stored in cold storage. All enclosures will have a slow rate of leakage and oxygen getting in due to microscopic flaws in the seals made. Despite this, we will not be monitoring oxygen levels over the short term. If it takes more than 5 years to start working on our improved anoxic chamber, then we will have to start up a program of annual microclimate checks and refreshing. When funds become more available, we hope to enter the main plan where the system is improved to an anoxic storage chamber. A dedicated portion of the cold storage will be nitrogen fed, pumping the excess and waste nitrogen from the pest management anoxic treatments into the space. Packing units will not require microclimate bagging system, regular checks and refreshing. At the current rate of acquisition and with the current capacity of the cold storage, we will run out of cold storage space within about 5 to 10 years. At an estimate, only about 5% of the acquisitions are likely to be the high-risk plastics, so being able to properly identify the plastics will increase our storage capacity by 50 to 100 years. FTIR is desired to identify high-risk plastics. Until then, we err on the side of treating all plastics as high risk and putting them into cold storage. Even lower risk plastics will have a slower rate of degradation in cold storage, so there is minimal harm to the plastics, provided they are padded appropriately to avoid physical damage while they are brittle. At Auckland Museum, there is a Pacific dimension called Te Lewa. Te Lewa means to nurture the relationship, referring to the interconnectedness between communities, collection, space, and the museum. One thing that Te Lewa outlines is the importance of making the collection physically accessible for the Pacific peoples and stakeholders. This is part of ensuring that the museum is a respectful, relevant, and engaging place. Ways that Te Lewa is activated is in the way objects are cared for in-house and in providing, organizing, and facilitating community visits in line with the diverse cultural protocols. We are mindful of these in the development of this new storage system. Of course, this poses questions such as what will community access look like for these pieces? Questions around its potential to be publicly displayed. And moreover, is there room for a flexible approach when collections are accessed by Pacific people? The current system presents challenges to community access. However, when we get the final cold anoxic storage, which requires no bubble bagging system, access to collection and high-level storage will improve. So, in summary, the rate of plastic acquisition is growing, and we have come up with an innovative plan of creating an anoxic storage chamber using locally available resources and expertise to meet the needs of the collection in a sustainable way. However, changes over recent times has compelled us to be flexible with our plans and move to Plan B of microclimate anoxic packaging, which still addresses our duty of care to our collections and our communities and stakeholders. In the long term, we hope to be able to upgrade to Plan A that serves both our source communities and our own needs more efficiently when circumstances allow. Te lava.
Thank you so much. Our second talk is with Christina Elsässer, Also in a recording, Christina Elsässer, who is a conservation scientist at the Deutsches Museum in Munich, where she is pursuing a PhD on the effectiveness and harmfulness of various storage conditions below room temperature on three-dimensional cellulose nitrate objects.
Thank you so much for the kind introduction. Today I want to speak about cold storage project which is currently taking place at the Deutsches Museum. The starting point of this project was that currently our main building of the museum is under refurbishment, meaning that every single part of the collection needs to be documented, packed and transported to the storage area. In addition, our existing storage area are improved. Several teams are working on that task, as you see on the picture, and they handle a huge variety of objects as well as plastic objects. Until now, objects which are assumed to be cellulose nitrate or cellulose acetate are separated and analyzed by FTIR spectroscopy. Those objects which are cellulose nitrate are then stored in this container at a yearly average temperature of 17 degrees. This has already quite a positive effect because this container is well ventilated and the cellulose nitrates objects are separated and do not cross-infect other materials of the collection, and they are easier to monitor in this container. But to prolong the lifetime of such objects, maybe a cooler temperature are needed. Cold storage has quite a long history with film and photographic material. Since 40 years, it is recommended to store them below 10 degrees to prolong the lifetime and to minimize the risk of fire. For lower nitrated three-dimensional objects, as we have them in our collection, it is as well recommended, but not yet common practice. As a result of a questionnaire which we were carrying out in 2019, only 4 institutions are storing some parts of their cellulose nitrate collection below 8 degrees Celsius. And I'm very happy because delegates from 2 of the institutions are invited speakers today. You might already have heard Valerie and Ruby from the Auckland Museum, and you will maybe hear in the following talk Marai and Capuchin, who implemented cold storage for Greek shadow puppets at the British Museum. For implementing cold storage at the Deutsches Museum, we still have and had some questions. Can any kind of three-dimensional objects transfer to the cold, no matter which, if they have different geometries or containing mixed materials, or are in severe or in good condition? How cold is a cold storage effective? What about condensation and the relative humidity? And how quickly can I transfer my objects to the cold? See some examples of the collection of the Deutsches Museum. So you can find cellulose nitrate in casings material of a scientific instrument or as printed scales, for example, in this radio. But you find as well cellulose nitrate in the musical instruments. So everywhere where you have such a pearlized look, it could possibly be cellulose nitrate. But you also find cellulose nitrate, of course, in dolls and combs. And the Deutsches Museum has a huge collection of product references, as you see in the last 2 pictures. The Deutsches Museum has a huge variety of objects. In the project, we want to test at which point the cooling of an object could become problematic. To gain a reproducible and great amount of samples where we can test cooling parameters, we decided to produce our own specimens. First, we wanted to test basic parameters at a plate with uniform material thickness. And I was really surprised that this kind of plate could as well be found in our collection. For example, in this booklet containing product references, or in this model of a bridge where transparent plate symbolizes the water surface. For the other designs of specimens, we wanted to be as close to the collection as possible. So we went to the collection and asked ourselves which kind of shape could we gain from the objects and which shape would be suitable for cold storage tasks. So how would you simplify the shape of a children's rattle, a doll, and a ping pong ball? And these objects might be simplified to a hollow plastic, like it's in the ping pong ball. But we thought for cold storage tasks, it would be more interesting to have different kind of material thickness in the sample. So we decided not to take this kind of shape. What else do we have in our collection? Is, for example, a lot of combined materials, as you see here in the musical instrument. If we have a closer look to the music instrument keys, you see that is a combination of cellulose nitrate and wood. And you might simplify such object to a veneer attached to a wood stick. But usually this kind of veneer is glued to the wood, and this would add another variable which we did not want, so we did not decide to take this shape. Now, what did we choose for specimens? So for different geometries, we took as an example cones, because we do have a lot of them in our collections, and simplified this shape to this kind of spires. And hopefully we think that the different material thickness from the spire to the base would cause stress during the cooling process. With mixed materials, we considered our huge collection of eyeglass frames, as you see here, and this shape could be simplified as a cylinder with a metal rod inside. And as metal, we have chosen nickel silver because it's widely found in our eyeglass frames collection. How the specimens should look like, we just needed to produce them. For the plates, that was an easy job. We bought transparent plates from a British company, Rothko and Frost, and just cut them in the right dimension, and we drilled a hole inside so that we can hang them up in the climate chamber for better ventilation. For the other two groups, it was much more complicated because we needed to transfer the plates to the geometry we wanted to, and that we could just do by pressure molding. But still, the process needed to be tested, and that was done by a master student, and she was, at the end she was successful, but it needed several trials. That's how the specimens look like after molding, and that are the final results. This next step was to produce specimens in different conditions, and this we wanted to do by artificially aging. Again, different conditions, we artificially aged our samples. For the plates, for example, we did an artificially aging at 70 degrees and 75% relative humidity in a climate chamber. So we hang up our plates on a glass rod so that they are well ventilated, and left them in this condition for several days. We did different kind of trials, and not everyone was successful. But at the end, we gained a deformation of the plates. They got yellow and got some bubbles, but as well they cracked. So I was very happy about that. So we do have our produced specimens, but we also have de-assessed naturally aged reference objects like eyeglass frames, combs, or transparent plate, and we want to expose them to cool and cold storage. Before testing the effect of cold storage on the specimen, we needed to know how we want to do that. So we decided to characterize our specimen with chemical analysis, imaging method, and mechanical testing. But I do not want to speak about mechanical testing today because we are just putting up our experiments. So it's too early to speak about that. For the chemical analysis, the main mechanism of degradation of cellulose nitrate are important. The main processes are the denitration due to hydrolytic loss of nitro groups, chain adhesion, and the loss of the plasticizer camphor due to sublimation. Due to this degradation, the object starts to emit nitrous gases, which could form with humidity acid drops on surfaces. Due to the embrittlement of cellulose nitrate due to chain adhesion and loss of camphor, they start to crack and typically form such square pattern crazing, which you see here on the picture. To evaluate different storage temperature, we did different kind of trials which analytical technique would be suitable for us, and decided then for ion chromatography for the denitration, gel permeation chromatography for chain adhesion, and the loss of camphor. We just addressed 2 papers lately on that topic, which hopefully be published soon. Let's proceed with the imaging methods. With the imaging method, we wanted to assess the evolution of cracks and if cold storage would induce further cracking. On the picture and the mapping under it, you see the evolution of cracks over 2 years at room temperatures. If you need to transfer such a heavily damaged object to the cold, would the cooling process causes more stress and maybe induce further cracking? Which methods would be suitable to assess it? So we have chosen photoelasticity for the stress distribution, and for the inside cracking and the monitoring of inside cracks, we have chosen computed tomography on a microscale. On the left, you see an artificially aged plate. On the right, you see the same specimen between cross polarizers. What you see is that cellulose nitrate becomes birefringent when it's stressed, meaning stressed areas become a little bit whitish or lighter, as you see on this picture, while non-stressed areas are darker. If you have a closer look on this area, this is pretty dark. And if you see here, it is a cracked area where the cracks already led to some kind of relaxation in the stressed area. Let's proceed with the last method I wanted to introduce today. That is computed tomography. And thankfully, we could realize our first scan with the Fraunhofer Institute. So we took a naturally aged object, as you see here, a fragment of that, which showed cracked and non-cracked areas. And if you turn now this object, you see the cracked areas, they are more whitish to the non-cracked areas, which are transparent. So this fragment was scanned by a mobile CT equipment of the Fraunhofer. You see the sample here in the picture in front of the detector. And what we gain is a 3-dimensional picture of density throughout the sample. From the computed tomography scan, you gain a lot of around 1,000 of section pictures. And if you have a look on this picture, it's taken from right from the middle of the object. You see that the cracks develop from the middle to the surface, but are usually not breaking through the surface. What else got visible is that you have region of higher and lower density. For example, here you have lower density region or cracks with lower density so that they appear dark. And above here you have region with higher density which appear whitish or much lighter. What could be the reason for this higher density region? Actually, it looks like that this higher density accumulates in cracks and are forming as well a crack pattern. So we do have a guess. So let's have a look on the microscopic picture. This is the same sample under the microscope. And if we have a closer look here, it is a cracked region which appears a little bit whitish due to the reflection of light. While the upper part here is a cracked region which appears a little bit greenish. The greenish shading might be due to corrosion products resulting from the nickel-silver alloy which is used in the temple of this eyeglass frame. It seems as if corrosion products accumulate in cracks and are the reason for the region of higher density, which are clearly visible in the computed tomography pictures. But why do we want to know all this? Because we need to understand the evolution of cracks in cellulose nitrate and how this would be changed by the cooling. Coming back to the project and where we are right now. So we do have our specimens and we have chosen another method with which we want to investigate different kind of cooling rates and storage temperatures. Our next steps are to carry out short-term experiments to check the effects of cooling and warming rates, as well to expose our specimens to long-term storage to evaluate the effectiveness of different kind of storage temperatures. I hope our results lead to guidelines for museum, which kind of objects and how they are best transferred to the cold storage. Thank you very much. I wanted to thank all the fantastic people who contributed and helped me with the SweShips project. The literature which I'm referring to on the slide can be found here. Finally, I want to say thank you for your attention. I wish you a nice conference, stay healthy, and I'm looking forward to your questions.
Thank you so much. Our third talk is with Marij Huck and Capucine Korenberg. Please turn on your video. Hello.
Hello.
Marij Huck is currently a conservation scientist at the Swedish National Heritage Board. Her areas of expertise include scientific investigations of cultural heritage and conservation methods with a focus on organic materials. Marij is the Swedish National Coordinator for the European Research Infrastructure for Heritage Science. And Capucine Korenberg is a conservation scientist at the British Museum. Her research focuses on assessing the suitability of conservation treatments for artworks and antiquities and understanding their deterioration processes with a view to find better ways to preserve them. She is currently working on laser cleaning and microfading. Welcome.
Thank you for the introduction. Thank you. So, are objects made of cellulose nitrate, sensitive to UV filtered light, and is it safe to store them in a freezer? In 2012, when Marai and I had to consider these questions, we discovered there was very little guidance in the conservation literature. In 2012, the Money Gallery at the British Museum was refurbished, and our procedure at the British Museum is to appoint an exhibition conservator for each new gallery or refurbishment or touring exhibition. This person will overview all aspects of conservation related to the objects that will be included in the exhibition. Next slide, please. So the Money Gallery traces the history of money from more than 4,000 years ago until now. And during this time, money has taken many different forms, from coins to banknotes, but also shells to mobile payment. So the exhibition conservator asked us to look at some plastic objects that were part of the new display. Next slide, please. And these selected objects were a flexible, transparent envelope. You can see on the top left corner, it was used to contain a gold ingot. Then we had some Iranian marriage token in a textile bag. And the token looks like gold, but they're actually cheap painted plastic coins. And the bag is made of a synthetic material. Then we had this very pink piggy money box. And this badge from the 1980s saying, I'm a NatWest piggy banker. And just looking at them visually, we saw that the envelope containing the gold ingot and the piggy money box showed no signs of deterioration. But this was different. I mean, you can't see it on the picture now, but the marriage tokens and the bag containing them showed some signs of discoloration. And the badge, the NatWest badge, here is very visible on the photograph. You can see this brown discoloration all around the edges. Next slide, please. So just showed briefly how a badge is made. So we're clear where the plastic is. So, a badge is made of 4 components. You have the pin back, the shell, and on top of the shell, it's not shown on the PowerPoint, but you have your design, usually on paper, and then you have your clear plastic cover on top. And this is all put together using one of these little pressure equipment. Next slide, please. So just after the new money exhibition opened in June 2012, the curator added 2 additional badges. And these badges that are shown here, they were older than the NatWest badge. They were actually from the end of the end of the 19th century. And we know that before 1920, the only widely available, commercially available transparent plastic was cellulose nitrate. So there was a strong suggestion that these were, actually, the very, very high likelihood that these 2 badges were made of cellulose nitrate. Next slide, please. And at the same time, in 2012, we had a very successful exhibition touring around the world. It was called History of the World in 100 Objects. And some of these objects were rotated every time they go to a new venue. And at the same time, the curator of this exhibition decided to include very similar badges to those that I've just shown you. So now we had 3 badges to consider, and this is when we decided to do a proper investigation. Next slide, please. And the outcome of this research is not going to be helpful for just these 3 badges, but much more relevant to the rest of that collection, because we have around 3,000 badges at the British Museum, and about 600 of them are a date from prior 1900, so most probably with a covering film made of cellulose nitrate. Next slide, please. Thanks.
Okay, I think I'll take over here from Capucine. Thank you very much. So we bought these surrogate badges for experimentation, and as Capucine has already mentioned, they were then identified as cellulose nitrate. At the same time, we also considered cold or freezer storage for other collections, and this was briefly mentioned by Christina Elsässer, that we have a Shadow Puppets collection that at the same time was considered for freezer storage. Now, cold and freezer storage is an accepted method for film and tape and negatives, but the potential differential shrinking due to freezing of composite objects, such as these badges, with a covering film and of cellulose nitrate and a metal base, was of concern, and therefore the suitability of freezer storage was also investigated. So this table shows the analytical techniques and the results for the objects that went on display in the new permanent gallery. Fourier transform infrared spectroscopy was used for the identification of the polymer types. X-ray fluorescence spectra were obtained for identification of metallic components and the inorganic elemental composition of the alkyd paint. AD strips were used for monitoring of acidic off-gassing, and ODI tests, which is an accelerated aging test, were conducted on a few unregistered objects to evaluate the potential to emit harmful volatiles. Surface swabbing and swab analysis by ion chromatography was carried out for the assessment of surface levels of some salts. This was done actually externally by Gemma Mitchell at the University of Strathclyde as part of a collaborative Heritage Smells project that was going on at the same time. The transparent envelope was identified as polypropylene, which is generally inert and stable and gave no immediate cause for concern. The Iranian marriage tokens had a polystyrene bulk, which again should not present any immediate conservation issues. However, the alkyd paint on the tokens appeared unstable, as 10 of the 41 tokens were already severely discolored and only 1 or 2 years after production. So in addition, the tokens showed acid off-gassing as indicated by the AD strips and the ODI tests. Further discoloration can be expected to occur, and recommendations were made that the badge and tokens should be inspected by a conservator at regular intervals. Now the bag has actually been removed from display. The money box pig was identified as polyvinyl chloride, PVC, with a stopper of polypropylene. The PVC material is relatively rigid, indicating that the content of plasticizer, if present at all, is low. The money box was manufactured in 1996 and appeared stable when investigated in 2012. There was no stickiness or other signs of plasticizer migration. And despite already having been displayed for several years, there were no visible signs of fading. And the money box pig is still on display today. The components of the piggy banker badge raised no particular concern, although AD strips indicated some acidic off-gassing. The metal base and especially the pin are corroded, causing staining of the paper that is visible from the front of the badge. The staining was compared to previous photographs and there had been no apparent change over 2 years. Now, another 7 years later, the badge is still on display and apparently unchanged. The 2 political campaign buttons were analyzed by XRF only, showing that their metal bases were of iron. The early date of manufacture, late 19th century or early 20th century, and literature research on the manufacturer, the company is called Whitehead and Hogue, left no doubt that this plastic covering film was cellulose nitrate. Therefore, a recommendation was made not to include these badges in permanent display, as it was uncertain how vulnerable they may be, even to the low light levels of the display, 50 lux. They were removed after 5 months display. So we then purchased these surrogate badges for experimentation, and they were from the same company, Whitehead and Hogue, and from about the same time. FTIR analysis on those badges confirmed that their covering films are of cellulose nitrate. Of the 6 badges, 2 were kept as controls in the dark at ambient room conditions. Those are Greece and Bolivia on the left there. 2 were subjected to repeated cycles of freezing and thawing. Those were the badges San Domingo and Denmark. And 2 were subjected to accelerated light aging. They are the badges United States and Romania. The badges were inspected intermittently by optical microscopy, electron microscopy, visually, and by ATR, FTIR. The total light aging time of 7 weeks would be equivalent to about 136 years under 50 lux museum display lighting, although it's difficult to calculate that exactly. The 2 badges chosen for freezing were the ones that appeared most and least damaged, respectively. And this slide shows some of the damages that were observed by the microscopy. The San Domingo badge showed staining, surface scratches, and 3 distinct areas of microcracking, while the Denmark badge exhibited the least stained and least scratched surface, next to no microcracking. The other 4 badges had some staining and scratches, but also almost no microcracking. Microcracking was also examined by electron microscopy. And it's important to note here that the partial vacuum during the SEM investigation did not cause any increase in cracking. Specific areas of cracking were imaged by optical microscopy before and after exposure in the SEM chamber, and no differences were apparent. The prolonged exposure to the electron beam, on the other hand, caused some surface marking, as is commonly seen with organic materials. The ATR-FTIR spectra of the control badges and those exposed to light aging and repeated freeze-thaw cycles showed no differences. After 1 week of light aging and 1 freeze-thaw cycle, there were no apparent changes. At the following inspection, after 4 weeks light aging and 2 freeze-thaw cycles, the white backgrounds of the light-aged badges were noticeably faded, but no changes to the badge cover film surfaces were noticed by optical microscopy. Similarly, at following inspections after 7 and 11 freeze-thaw cycles, no changes in cracking were observed. The light-aged badges were somewhat faded, but whether there had been a further change between 4 weeks and 7 weeks light aging was not visually apparent, and no surface changes before or after light aging were noticed under optical microscopy.
Excuse me, Marai, just one
Yes.
moment.
Mm-hmm.
Joana Lia Ferreira, please turn off your video. Thank you.
So you can see just about in this image that the United States badge on the lower picture appears somewhat brighter compared to the ones next to it, the San Domingo and Greece, whereas on the upper picture, before light aging, it is actually slightly yellower. Not so easy to see. The design areas of the badges were too small for direct color measurements. So therefore, the light fastness was further inspected by microphotometry. The microphotometer focuses an intense light on a spot of approximately 300 micrometers diameter and records any color change as a function of time. The tests were run for 10 minutes. The color changes of samples of ISO Blue Wool standards 1, 2, and 3 are also measured and used as comparative standards. Blue Wool 1 being considered very light sensitive and Blue Wool 3 of medium light sensitivity. A color change delta E value of 1.5 corresponds approximately to a perceptible color change. The results show that all the colors tested were more light fast than the Blue Wool 2 standard, except the red area on the Bolivia badge, which had a similar light fastness as Blue Wool 2. The results of the light aging and microfading experiments provide reassurance that even high doses of light exposure, as long as we're excluding UV, do not appear to cause any noticeable damage to the cellulose nitrate covering film, and caused very little color changes on the print design of the badge papers. So in conclusion, a selection of plastic objects from the City Money Gallery, as well as unregistered surrogate objects for experimentation, were investigated using FTIR, XRF, SEM, optical microscopy in order to identify the object's composition. They were subjected to ion chromatography, Audi testing, microphotometry, accelerated light aging, and exposed to freeze-thaw cycles to gain information regarding their stability, off-gassing, and light fastness. The clear envelope and the money box pig appeared stable, and no special recommendations were made concerning their inclusion in the permanent display. The Iranian marriage tokens and the NatWest Piggy Banker badge may be expected to show further deterioration, and care needs to be taken that their acid off-gassing does not cause harm to other objects in the same showcases. Initially, recommendations were made to remove 2 cellulose nitrate badges from display after a few months. Subsequent accelerated light aging and microfading tests on cellulose nitrate badges purchased specifically for experimentation showed that light exposure was of less concern than first anticipated. Exposure of the cellulose nitrate badges to freeze-thaw cycles showed that this is a safe method for the long-term storage and preservation of these vulnerable materials. Pre-existing cracks in the badges were monitored for any change after freeze-thaw cycles, but none were apparent, indicating that even brittle and somewhat deteriorated cellulose nitrate appears capable of recovering from temperature-induced shrinkage without further damage to the material. It should be noted that deliberately extreme conditions of freeze-thaw were applied during the tests, but suitable packaging, including humidity buffering materials and special vapor-proof films, would be necessary, and a conservator should be consulted before any registered collection items are transferred into freezer storage. Thank you very much, and I look forward to questions.
Thank you so much. Now, will all of the speakers who are available turn on their cameras, and we will be able to begin our question and answer period a little bit early, and therefore we might be able to take some of the many questions for everyone. I don't know whether Ruby is able. Ah, there you are. Wonderful. Great. So I will start with you, Ruby. We have, as a first question, have you been able to collaborate or partner on cold storage with other museums in your area?
Thank you. No, I have not. I'm not personally working on this project. In terms of what Val has mentioned about working with JED and creating their Noxic chamber, I'm not sure if they also collaborated with other museums in the area creating that system. But as far as I am aware, JED had invented that anoxic chamber that Val had talked about in a presentation.
Great, thank you so much. Christina, here's a question for you. This was a very well-rated question. A lot of people want this answer. Why do cracks develop inside the cellulose nitrate and do not reach its surface?
This is a very good question. Actually, it's an observation which had been made from several conservators. But why exactly is that the case? It is not known yet. So we have some guess, and we are investigating this case. We think that it has to do something with production and the degradation phenomenon. But so we made already some SEM, also scanning electron microscopy picture, and it's really clearly visible that usually the cracks stops short before the surface. So that could be due to that the surface might be dense, more dense because of the cooling processes during production, and as well as the degradation phenomena. But we are looking into this topic as well. So in the ongoing research, we will do trials or test our mechanical properties as well, imaging and chemical analysis from the surface and from the interior of this sample.
Thank you.
Sorry, I do not have a complete answer for that, but right now, hopefully in some years.
But now you have 314 people who will be helping you to find these answers.
That would be great. And as well, I mean, there's a Meet the Speaker chat room, and I'm on Slack, so I'm willing to discuss this, of course, later on.
Excellent. Now for Marai and Capucine, could you tell us more about how you're using AD strips in this context? For example, just as an indicator or in a similar way as intended for film?
They were used just as an indicator, and the AD strips are actually used by the conservator in the first assessment of those objects that are planned to go on display and that they might have concerns about. So before even the request came to the scientists to look more into those plastic objects, the conservators had already checked if there was some off-gassing with AD strips, and because they had seen some discoloration of the acid detection strips, they were a little bit worried about them. So really quite it's a relatively rough method. You enclose the object in a bag with the strip next to it and just check for color change.
Ruby, which temperature and relative humidity would your cold storage have, and for which kinds of plastics? There's another question in there. How do you deal with composite materials like plastic and metal?
Thanks for the question. So I'm learning as I go, and I asked the same question and I was told the colder the better. And so the storage that we have at the moment is the coldest that we have is 2 degrees Celsius, which is what we use here. And that's the best that we have at the moment. And so yeah, that storage is earmarked. It's storage that the plastic collection that we've been talking about is earmarked to go into. But yeah, I was advised just the colder the storage, the better for these plastics, and that's why they were encapsulated in foam, so it's supported in all areas, so that any kind of movement wouldn't have so much impact on each of those fragile pieces. And yeah, and I don't have a lot of experience working with metal objects, so that's definitely a question that Val, the conservator from Auckland Museum, she would be very happy to answer that question as well.
Great, maybe we can pose that to her on a Slack channel, or maybe you can let her know that people are interested in finding out. But maybe Christina, you'd like to speak to the colder the better question, because that's a little bit what you mentioned in your talk. Do you have an opinion?
Yeah, of course, for the chemical point of view, of course, the colder is better. The problem, of course, or what I want to investigate in my PhD is at which point it might harm the object. That means when, for example, for composite materials, for example, metal and cellulose nitrate, where metal has difference coefficient of linear expansions, how that could stress the objects and increase maybe cracks while cooling down the object or transferring from the cold to back to room temperature. So yeah.
There's a question for you that's connected to the question that we heard for Ruby a couple of questions ago. Are you collaborating with other museums for developing the guidelines for cold storage 3D cellulose nitride objects?
Until now, we are at the very beginning, but we are planning, as I said, to develop guidelines. Until now, I set up within the Leibniz Association working group with the different research museums, where we want as well to set up these guidelines. But we are, of course, open for cooperation on this topic, and yeah. So just do not hesitate to contact me, and I would be very glad to cooperate even more.
Great. All right, Marij and Capucine, do you know the composition of the white particles on the badges seen under SEM? Or
yes. Yeah. In the electron microscope. Yes, I did some mapping of those areas. Mainly it was calcium. I'm assuming calcium carbonate. There was some potassium and manganese also. It was different on different badges actually. But because I also had no particular explanation where they came from, other than maybe dirt that accumulated in the cracks, there's no way of telling if it's coming out of the badge or if it's dirt. Yeah, well, actually thinking back to it, you can. I mean, you can see what's next to it, obviously, if there is some calcium or magnesium, potassium. I don't think so. I think it was dirt. I think that was my conclusion. It's a long time ago.
all right, let's take a question for everyone, and you can answer as you see fit. Sustainability is a tricky question when it comes to cold storage. For one side, due to the costs, and for the other side, due to the lower accessibility from the stakeholder or for stakeholders. And also, making things cold is an energy-sucking enterprise. So what is your opinion about it, and how maybe have you solved some of these problems in your museum contexts? And then maybe this is more aggressive. Should we even continue to research in this field if we know that it affects sustainability? Take it away, anyone who wants to.
Should I start? Well, I don't work at the British Museum anymore, so I can't really answer for the British Museum, but at the time, there was very little cold and freezer storage, and we actually ended up only putting the Shadow Puppets collection in a chest freezer, which, looking at all the energy efficiency of the different types of freezers, a chest freezer seemed to be the most efficient way to go. And even though we deemed it was a safe method for the badges, they still have not been put in a freezer, whether that's because of lack of interest in the collection or because of it's not energy efficient. We'll see. But there was definitely a lot of interest in the Shadow Puppets, and they were deemed a very important collection of some political badges, puppets from the 1970s. So they are in freezer storage, and it's well for them.
I think, I mean, the badges didn't go into cold storage. There was a lack of resources. And also we had a changeover of the curator of the money gallery, so in charge of the badges. So they had different priorities, but it's not a question of sustainability. I mean, in my personal opinion, we use cold storage in lots of other industries for food. And so I think preserving our cultural heritage is so important that I would continue investigating this. This is my personal opinion. It's like also when we talk about air conditioning in galleries, when you think about all the shopping malls, all the cinemas that have air conditioning 24/7, I'm not sure we should worry so much about it, because our culture is really important, and it's great that if we can preserve it for the next generations.
I'll step in there and say I agree with your point there that it's sorry, this is Val Tomlinson here. I don't seem to be able to video, but I am actually present. So yes, it's how much do you value your cultural heritage? So it's you balance. It's a cost benefit analysis. Like you want to preserve your stuff as long as possible. You have to have the expense on the less sustainable side of things. And I guess the other thing I was going to say about the sustainability aspect of it is the identification of the plastics is very important there, because you can limit the stuff going into cold storage to the stuff that really, really needs it to preserve it. And you're cutting down on the volume of stuff that's going into cold storage that way by knowing what the plastic is and whether it will benefit from the cold storage. Or, well, whether it will benefit significantly from the cold storage. Everything benefits in reduced aging rates with cooler temperatures. But yeah, there's only that limited list of plastics where it's really important to have things cold and anoxic.
Christina, do you have an... Oh, sorry. Go ahead, Ruby.
I'll just quickly add to that, just an example of the collection that we were talking about in our presentation. These pieces are very, very important because we actually see the way that Pacific people are now being innovative in their practices, because they have migrated to another country where they don't have the traditional materials that they would normally have to create leis or necklaces. And so you see that they're moving into a new country. They're also finding different resources of how to continue their cultural art practices. And so that's why these pieces of necklaces were acquired for the museum, and it tells a story of a group of people at a certain point of time, and it showcases all the ingenious practices, the way that they weave things together, the way that they create these leis. It's very important, and so it's just to put some further context into why it is important to continue the work that's been done by each of these wonderful ladies, and also by Val. And so that's my personal opinion, that this should really be continued, because it'll be very, very good for the future generations.
Thank you, Ruby. Christina, do you have an opinion?
Of course. I mean, I'm doing a cold storage project. So actually, from this point, of course, I'm totally agreeing with my speakers before. So at the moment, cold storage is nearly the only option to prolong the lifetime of cellulose nitrate objects. So of course, I think it's worth to store them in the cold. And and at least, I mean, maybe not for every single piece of cellulose nitrate, but for the objects which have like the puppets from the British Museum, or which has a value, a very great value. I think it's needed.
Thank you so much. This was a nice little roundabout discussion. And Val, if you need to say something, just shout it out. I can't see you, so please just enter in whenever. I now have a question for both you and for Ruby. How long can the PU foam used for the packaging last? Do you have any experience, and how sustainable are the barrier films used for encapsulation? I think this connects a lot to the Harvard talk from last week, where they were also encapsulating and putting things in different situations.
So just let me clarify your question here. You're asking how long the barrier film itself lasts, because it too will age and degrade at a particular rate. Is that what you're asking?
Well, the wording is, how long can the PU foam used for the packaging last? Do you know?
Okay.
And then how sustainable are the barrier films used for the encapsulation? I'm not exactly sure what is meant by sustainable, but maybe you can answer it broadly.
Okay, well, my understanding of PU foam is that's polyurethane foam, so like upholstery foam, which tends to have a very low lifespan, but it's not used in museum packaging normally. It's usually the ethafoam that is used in the museum packaging, and it's a different plastic with a longer lifespan. So my understanding of things like polyurethane foams is that they can crumble within a matter of decades.
I think the question was that there is a foam layer that's surrounding the leis as they're placed into their,
Okay.
and is that correct, Ruby?
Yeah, that's the
It must be the
ethafoam. So it's
Tyvek.
not polyurethane, it's polyethylene.
Okay,
Yeah. So
we've
yeah,
cleared that up.
polyethylene has a longer lifespan. It too does embrittle with age. But I haven't noticed a lifespan to the ethafoam in my time in museums, but I would presume after 50 or 100 years you'd want to replace it. So yeah, I don't know actually the lifespan of the museum materials that we are using at the moment, but they will have a lifespan and they will need to be replaced eventually. And the barrier film, so I'm presuming there you're talking about how often we want to like open them up and replace our ageless inside for leakage rates, and because we're hoping to upgrade in relatively short time span to having an anoxic chamber where we're using our nitrogen generator. We were hoping that we could do the ageless encapsulation only using it for a relatively short period of time, so we weren't going to bother with using an ageless eye or an oxygen sensor. We were just going to say, if it takes longer than 5 years, then we're going to have to do something different to get our new system in place.
Thank you. Ruby, did you want to add?
No, that I feel like she's covered that for me as well. Thank you.
Great, thank you. I think it's interesting to see that there are solutions for time, and I think we're all solutioning for time during COVID and in all of the different ways that we're trying to figure out where the future is going. Next question for Christina. Did all your cellulose nitrate samples contain camphor, and will you quantify retained camphor and hence plasticizer loss in aged samples?
Yes. So as well, we did do a survey on the cellulose nitrates objects we have in our collection, and all three-dimensional objects until now do contain camphor as plasticizer. So we have chosen to as well have camphor as plasticizer in our cellulose nitrate specimens. So what we do is actually to quantify the camphor amount with gel permeation chromatography before and after cooling. So yes, So we consider this.
Great. For Capucine and Marai, which method do you think is most suitable for future analysis?
That's a very broad question.
Indeed.
Because I mean, to identify plastics, we found that the FTIR is the most straightforward. We've trained some conservators to use it, so they can identify plastic without an input from the scientist, which is great. So I'm not sure what the question what it's about, if it's I mean, if it's what's the most suitable technique for research, to look at the degradation of plastics, I'm not sure.
Yeah, it's a very broad question. But I would say to follow Christina's project is a good way to go, because they're really doing this in depth and much more thoroughly than our quite quick investigations. So I'd follow their results.
Great. Now for Ruby and Val, are there any plastics that you have found do not respond well to an anoxic chamber?
I'll answer that when I'll answer that with saying we can't answer that because we are only just starting our project. We haven't gotten to the point where we're actually got things in anoxic conditions with any length of time, really. So we can't answer that question yet.
But you do know that people are waiting for the answer. So let us know whenever you have them.
Yes, that will be our next installment.
Great. Christina, please tell us about your research plan or your research strategy. With whom do you work and how do you make decisions as a team? This is kind of a more manage your research project process. I think it might be helpful for other people if they want to replicate it in some way.
Oh, okay. I hope I can answer this satisfactorily. But you have the chance to actually meet some parts of our co-authors, so Marisa Pamplona and Teresa Donna and Veronica Meyer, in our Meet the Speakers after the session. But actually, so we do have, from the very beginning, we have cooperation partners of this project, especially the Technical University of Munich, where my PhD supervisor as well, Professor Christian Große, has his chair. And we do as well have a cooperation with PSS, that is a company who actually provides this geopermeation chromatography systems. And as well, we are, as the Deutsches Museum, in this Leibniz Association as a research museum. So we do have several kind of partners. We try to have regularly meetings and discuss our questions in this kind of meetings, and decide the best way to go on these research topics. But for more details, please just contact me. And I hope I answered a little bit of the questions.
Great. I think it's interesting for people that you're working with so many different groups, Fraunhofer, et cetera, and how do you manage all of these different connections, and what is the process of getting them also, perhaps, if you could speak shortly to that.
So, for example, the Fraunhofer is a good example because it's so we have this question: how can we do computer tomography pictures to get an insight into cellulose nitrate samples? And yeah, actually, I'm not totally sure how we got to them, but yeah, in this case, I think it was as well luck. So we asked them, they were at the Deutsches Museum anyway doing computer tomography pictures, and so I could step in that. So it's a combination between luck and be on the right place at the right time. So I was very happy that they could conduct a computer tomography picture for us. But yeah, so at the moment, I'm very happy that a lot of people are willing to help and to assist. And yeah.
Thanks. Capucine, you were nodding a lot. Do you have some ways of strategizing about research that involves not just people on your own in-house team, but other institutions that might be helpful for our viewers?
Well, I find that generally people are interested in research in cultural heritage, like people from other backgrounds. When you write to them and say, "Oh, I work at the British Museum, and I would be very interested to see if the technique you're developing could be used on some part of our collections, especially if it's interesting objects." People are usually enthusiastic. So that's my experience. And sometimes it's really nice because sometimes they view things from a completely different way. So getting a fresh perspective on problems, it's usually a good thing for research. So
I think we saw that in the example of wine making industry in Ruby and Val's talk, how it's beneficial to just take from what is around you to make it work. I have another question for you. Very specific. Did you observe any condensation on top of batches after freezing cycles?
I deliberately wanted condensation. I chose the most extreme and not to recommend method of freeze-thaw cycles, actually putting them openly in the freezer and out again and in and out and in and out, without any buffering or packaging, or so the fastest thawing and the fastest freezing, and yes, condensation, because I wanted to test the extreme case. And if we'd have seen any of those badges popping apart or the cracks opening more, then that would have answered a question. But to my surprise, not even the micro cracks moved. Nothing moved, nothing changed. 11 times in and out of the freezer. Yeah, I would still recommend not to do that. I would recommend to use a buffering material, a proper case, and a vapor film, of course, and to slow the thawing and everything. But yeah.
You also worked with the manufacturer to get your samples, correct?
For me, no, I looked them up. It says on the back of the badge, it's printed that it's produced by Whitehead and Hogue. I don't think this company exists anymore. This is an 1890 something company. But just looking into that company, they used cellulose nitrate. And then on eBay, we purchased surrogate badges from the same company. Very cheap.
So you purchased them from eBay, not from the company itself. Have you had experience working with the companies? This is maybe more...
I don't think they exist anymore. I don't know.
But perhaps any companies that might still be in existence. This was a topic yesterday about whether you can connect with the manufacturers.
I think Christina can answer that better than because they really looked at buying from manufacturers.
So actually, so with the we pursued, we bought some cellulose nitrates from the company Rothko and Frost, and I was actually asking them because they're of very limited thickness, so 0.5 millimeters. I asked whether we could gain or get thicker samples from them. And the answer was, yeah, if you just ordered 100 tons, we can talk about that. So, and that is maybe an example how the communication, so they're, yeah, they are not very open. And I explained several, tried to explain my case that I needed for research, and I would be very happy. And if I gain more information about that and where they get it from and how they produce it, but they were, did not really answer. Yeah.
Great. Val, if you turn on your video, then our producer Jenny can pin you to our conversation if you're still there. If not, we are enjoying your voice. So next question is for both of you, Ruby and Val. There we go. How wonderful. Excellent. Is plan A to create a storage space that's both cool and anoxic? And if so, what kind of access protocols will you need?
Yes, the plan was to create within our existing coal stores at least section off part of it so that we could have cold and anoxic. And yes, part of the plan we would have to have oxygen centers in the surrounding rooms to make sure we're not going to asphyxiate ourselves and have alarms and that kind of thing. But until we actually get to building it, then we're not there yet. So yeah, that would all be part of the planning of how to build it. Because well, like I mentioned in my talk with Jed's pest chamber stuff, he's added on humidity control to the nitrogen flow. He's got oxygen sensors, temperature sensors that are all, so you've got RH, temperature, and oxygen that's being monitored in the nitrogen flow that's going into the chamber. So we'd have to do the same sort of thing with our cold anoxic chamber, is that we would be wanting to measure and control humidity, temperature, oxygen levels inside the chamber, and then we'd have to have alarms and safety sensors outside the chamber.
Great, thank you. All right, Christina, how did you determine the time, temperature, and humidity level during the aging?
A good question. So we did several trials with the plates first. So that we get the same, or that we get, we wanted to achieve cracks, or we want to age it until we might get cracks. And so we did some just basic trials, when do we get them? And the humidity and the temperature was controlled by our climate chamber. And we put in several data loggers to control the relative humidity and temperature inside the chamber externally as well. And yeah, so actually, and then we chemically or did chemical analysis for the degree of nitration, the loss of camphor, and the molecular weight before and after aging.
Thanks. For Marij and Capucine, is the that we just had that, sorry. What type of equipment did you use to monitor color fading? A colorimeter? And this person asking the question, who I don't know exactly who it is, it says, I always have problems with bright surfaces with a colorimeter.
Well, we use our microfading equipment. So, I mean, during accelerated aging. So it's just, but as Mara described, it only measures a very small area, a third of a millimeter. And we do the measurements so that we don't get any reflection. So working with a glossy surface is not a problem. So I don't know if it answers the question.
Well, you will get questions perhaps in, go ahead,
Yeah.
Marai.
Yeah, I could just add, it's by colorimeter, most people mean the Minolta, maybe the handheld one that you put directly on top of an object. And that one, the smallest size for measuring is 3 millimeters diameter. And that was too big for the badges. That's why we moved to microphotometer. And the setup is that it's a spectrophotometer with a fiber optic cable. And the optics, as Capucine described, you don't measure specular reflectance. So you measure at, was it 45 degrees?
Yeah, 45 degrees.
Great, thank you. I think this is the last round of questions before we go into breakout rooms and people can ask very direct questions of all of you. Val and Ruby, do you use a material other than Tyvek for packing sticky surfaces?
No, that's basically the material that we use at the museum for packing all of our objects. We also use a lot of tissue for buffering, but yeah, our priority would be, we feel like Tyvek is the final and probably the main packing supply we would use when packing. But that's for myself. I'm not sure if Val could answer differently.
Yeah, I was going to say if it's specifically the sticky concern that we use Tyvek for most of our packing, but if we're specifically concerned about stickiness, then we would probably put a Mylar barrier between things.
Great. Christina, this is the lightning round. Could you describe the method of observation your samples between crossed polarizers? Is there any article how to make these photos, and could you share it?
Until now, I do have some. So, in our field, there is, I did not find a protocol for that right now. So I would be very happy if you, could provide, or anyone could provide that. But it's a well-known technique. For example, for what is the English word? Sorry, for
just say it. I can translate.
Zahnmedizin.
For dentistry.
Yeah.
For prostheses or crowns.
Yeah. So there I found a little bit literature connected to that. So that, but they are not so very helpful. But I can, of course, put up a literature list, and I might have I misunderstood the question before. It might was addressed to the relative humidity and the temperature, how we end up having this exact 70 degrees and 75% relative humidity. Was it more like this, or how we kept this temperature in our climate chamber. Wasn't sure.
Neither am I, so I hope that person goes and talks too. But Marai, you had something you wanted to say?
Yes, for polarizer films, it's you can actually buy them. You can buy about A4 size sheets from any kind of photography company. They're used as filters in photography, and then you buy 2 of them and place your object on a light table, for example, and then hold them at 90 degrees to each other over the object. And then you'll see effects. You'll see birefringent effects. It's it's very nice to look at cutlery, for example. Plastic cutlery looks in all rainbow colors. It's a really nice education tool.
That's a wonderful note to end on for our very intense question and answer session. We will break now for 5 minutes before we return to connect in digital space. During this pause, we'll be assembling the breakout rooms. And when you return in 5 minutes, you'll be able to choose from 3 types of rooms, meet the speaker, chat about a topic, and drink a virtual coffee, as was yesterday. And please make your choices when we return. You will also be able to stay in the main room, but it's not really a warm place because there's too much furniture. Namely, we have this slide up there. So if you want, it would just be great to go into breakout rooms. I will see you in 5 minutes, well, now 3 minutes, at 30 past the hour, wherever you are. Thanks so much.